All right, so we have, as I just mentioned, the exam on Wednesday. And so what I want to do today is go through a sample exam and be systematic about it at the same time to talk about the content of chapters 2 and 3. Try to basically do it in the order it comes. In the example we did last Friday, we were just thinking about an application and highlighting concepts as they came up in the solving of the application. It was the free fall problem. But this time, let's be more thorough and systematic. So here's an exam I gave back from fall 2019, exam 2. And so let's start with, what's the earliest stuff that we learned about in chapter 2? Well, remember what chapter 1 ended with. Chapter 1 ended with limits, which you should still know about. And in chapter 2, we transitioned into initially applications, talking about speed and distance traveled, for example, and the derivative, and how to find the derivative and how to interpret it, how to graph it, that kind of thing. So if you look back in this fall 2019 exam, which is on Moodle, we can find a problem that is related to derivatives and limits. In fact, a couple of them, and related to position and velocity. Maybe we should go ahead and look at this problem right here, right away. Problem number 13. It doesn't involve a limit, but it still emphasizes the derivative concept and its applications. I could phrase this problem so that it did involve a limit, and maybe I will do a limit here, but at the moment, it's just applications. Again, this exam is on Moodle, so you can certainly download it there. You may want to take screenshots of the questions themselves, just so you have something else to look at if you want, like on your phone or something. So here, this problem, we've got the height of a ball is a function of time. H is the height of the ball in meters. F of t is the function that tells you what the height of the ball is at time t. T is in seconds. Note that negative 4.9 is negative 9.8 divided by 2. That is not a coincidence. Times t squared plus 78.4 t. The 78.4 would be the initial upward velocity. So a very high positive initial upward velocity. I don't think you could throw it that hard. It would have to be shot out of some sort of gun or something. And from an initial height at t equals 0 of 3 meters. When t is 0, this would be 3. 3 meters is, maybe as far as you can stretch with your hand if you're standing on your tiptoes. Part A, find the average velocity between t equals 1 and t equals 3 seconds, including units. Part B, using the fact that the derivative is this, find the moment in time when the ball reaches its maximum height. That's what we were talking about last Friday. T max, the time that you reach the maximum height. And then part C, actually find the maximum height. So this problem, again, is not stated in terms of limits. I could have stated it in terms of limits. I could have said find the derivative by using a limit. We're going to save that for another problem, though. Let's go ahead and solve it. Anybody remember the definition of average velocity? Offhand? Do you add numbers? Do you divide them? Do you do more than one thing? Anybody remember offhand? You want to say it again? Distance over time. Yep. Because distance equals rate times time. The rate is the average velocity. If you multiply both sides of this by time, you would get distance equals essentially rate times time. Think about the units to help you as well. Distance is in meters, time is in seconds. You want your units for velocity to be in meters per second. And I am calling this a velocity, so it could be negative, though, since it's near the initial time, it's probably not. It's going up still, probably. Yeah, it will be going up. This is going to be a positive quantity. But if I picked from t equals, 5 seconds to t equals 10 seconds, it probably would be a negative velocity. Negative average velocity. This is change in position, change in h divided by change in time. We could use delta notation for it to stand for change in. The change in height is the difference in function values, f of 3 minus f of 1. And the change in time is the amount of time elapsed, 3 minus 1, 2 seconds. I'll just plug these numbers in my calculator. Maybe you want to have your calculator out, so you can check calculations. So plug in 3, I get negative 4.9 times 3 squared. I'm plugging into the function here, right there. Plus 78.4 times 3 plus 3. That's f of 3. And it is about 194.1. What that means is after 3 seconds, the ball is 194.1 meters high, very high. If it's a small ball, you probably wouldn't be able to see it anymore. F of 1, plug in 1 here. Maybe I can do that in my head. 78.4 times 1 is 78.4, plus 3 is 81.4. 1 squared is 1 times negative 4.9. 81.4 minus 4.9. Can I do that in my head? 76.5, I think. Somebody double check that? Yeah. Okay, thanks. So do that subtraction. That difference in the top is not the height, it's the change in the height. 117.6 meters divided by 2 seconds. Your average velocity is 58.8 meters per second. And it's positive, so the average, on average, you're going upward, and in fact, for this entire 3 seconds, you actually are going upward. I didn't ask for it, but I could have asked, interpret this geometrically. The graph of the height as a function of time looks like a parabola because it's quadratic with a negative t squared coefficient. It opens downward. This is 3 here. I don't know exactly how high it goes. We'll figure that out. This is t equals 1 and this is t equals 3. We've just figured out a slope of a secant line, a rise over run for that little straight line that I drew in there just now. Triangle to emphasize it, a right triangle here. I just figured out rise over run, the length of this side of the triangle divided by the length of that side. This picture is not to scale, okay? You should be able to interpret that geometrically as a slope of what's called a secant line. Secant line goes between 2 points on the graph. Part B, use the fact that the velocity is this thing. I could have had them find that with a limit, though it would have been a bit of a pain. I could have also told these students from the past, and I could tell you, calculate that velocity by using rules for derivatives. Differentiate this function. That's something you should certainly be able to do. I kind of wanted to avoid mistakes, so I did just tell them the answer here because I was more interested in the application in this problem. If you differentiate that, bring down the 2, you get negative 9.8 times t to the first, which is what you see there, plus 78.4, which is what you see there, plus 0, you don't see anything because adding 0 doesn't affect anything. Find the moment in time when the ball reaches its maximum height. Moment in time. Solve for t. Set the velocity equal to 0 and solve for t. Excuse me. Add 9.8 t to both sides to cancel it on the right side. Then divide both sides by 9.8. T is 8.4 divided by 9.8. And how about that? I made it come out to be a nice number. 8 seconds. Okay. I didn't have to make it come out nice, but I did. According to this model, this ball is going to reach the maximum height before starting to come back down after 8 seconds. It's probably not exactly accurate because we're ignoring air resistance. But if the air resistance is small, you would hope it's not too far off. That's what I called T max last Friday. It's really V0 over G. Hey, remember that? V0, initial velocity, over G, the acceleration due to gravity. But now we have numbers instead of functions. Part C, find the maximum height. That's the time of the maximum height. To find the actual maximum height, plug it into the function. Find the max height is going to be f of 8. Negative 4.9 times 8 squared is 64, plus 78.4 times 8, plus 3. And units will then, of course, be in meters. So negative 4.9 times 8 squared is 64, plus 78.4 times 8, plus 3. The maximum height is 316.6 meters. You know, you'd have to, when you apply mathematical models like this and you're wondering how accurate they are, you have to just compare them with experiment. Actually get some sort of setup where you're shooting a ball straight up in the air and you can measure its initial velocity and initial height, and you can compare how well this does. It's probably not perfect, again, but you hope it's not too far off. And this is in meters. By the way, you should be able to do the general case as well. The general height case, f of t turns out to be negative g over 2 t squared plus v0t plus h0 for the initial height. That's the general model where g is the acceleration due to gravity, but it would be different on the moon or on Mars. v0 is the initial velocity, which in general would be positive, but could be negative. You could be shooting it downward. And h0 is the initial height. You should be able to find, you could call it h max by plugging in t max in place of t. But what is t max? We found it last Friday. It was v0 over g. Should be able to simplify this expression to find how the maximum height depends on v0, g, and h0. You could simplify this. In fact, I could do it right now. Get a common denominator maybe of g, because you got a g squared down here, but that would cancel with one of those g's. You do have a g down here. Looks like, if I don't make a mistake, or maybe I should do a 2g because of the 2 there. If I don't make a mistake, maximum height would be, let's see, that g cancels, like maybe v0 squared plus another v0 squared with a 2, because of the 2 down there. I'm afraid I'm going to make a mistake or something. Oh, this is, excuse me, this is negative v0 squared. Making mistakes here. Negative v0 squared because of that minus sign. Then we're going to have plus 2v0 squared because we got a v0 squared there, and we get a 2 because of the 2 down there. And then plus 2gh0. Why 2g? Because I've got to multiply this thing by 2g over 2g. If you simplify this, it would be v0 squared plus 2gh0 over 2g. That is how the maximum height in this model depends on the acceleration due to gravity, the initial height h0, and the initial velocity v0. If I did not make a mistake, which I could have, but hopefully I didn't. You should understand the idea of that. Okay? And hey, that's something we could take partial derivatives of, but it would be more complicated. So let's not write the moment here. Can I clarify anything here? Question. Mm-hmm. Yep. Mm-hmm. Oh, that's what we did do, actually. We set the velocity equal to 0. I gave you the derivative. Set the velocity equal to 0 to find the time of the maximum height. That's what we found in part B, was the time of the maximum height. In C, you got to find the actual maximum height itself. You got to plug it into the function. Does that make sense?
I just don't understand why this function here is plugging that height or plugging the time.
Well, that's what I did right here. Don't plug it into the velocity equation because you already know it's 0 there. Plug it into the height function that gives you the height if you want how high it goes in meters. because that's the function that gives you the height. Does that make sense? Okay. If I put limits in there, it would be a mess. Here's a less messy limit problem. Number 10. Use the limit definition of the derivative to show that if f of x is x squared, then f prime of 5 is 10. And do notice we know from the power rule f prime of x would be 2x here. And if you plug in x equals 5, you do get 10. But that's not what I'm asking the students on this old exam to do. I'm asking them to use the limit definition, and I even start it for them here. Also, give short reasons. We did do problems like this before spring break, maybe early March or something, late February, early March, we did problems like this, and we talked about reasons. Let's review this. Give short reasons for each of the equal signs. Also, make sure you give a reason for the first equality, in other words, this one. If you had to give a reason for that first one, what would you say? Close. Definition of the derivative. But it does, of course, involve a limit. The definition of a limit is that thing that in the book that I kind of ignored, involving the epsilon and the delta. We did talk about it some, excuse me. We didn't talk about it as much as we could have, but we did talk about it some. That's the definition of a limit, but that's not what we're after here. This is the definition of the derivative, which is that's the most fundamental thing to know in the whole first half of the course here, is what is the definition of the derivative. Got to work at knowing these things, okay? Knowledge is important. Knowing things, yes, you could forget them, but you're going to remember how to look them up better if nothing else. That's a limit of difference quotient. In general, f prime of a is a similar limit except with an a instead of a 5. At each step now, just do what you can, so to speak. The only thing we can really do as a first step is just plug into the function. And you've got to understand function notation. That's why we emphasize it so much. You've got to understand what f of 5 plus h means. It does not mean, and I've seen plenty of people make this mistake, it does not mean f times 5 plus f times h. F is not a number. F is a function name. It's a conceptual difference. Its output is a number. F of x is a number, but f itself is just a name. It's a name for the function. F of 5 plus h means go to the formula for f, and wherever you see the variable, in this case x, replace it with 5 plus h. So you've got to do 5 plus h quantity squared. That's f of 5 plus h because the function is x squared. If the function were x cubed, it would be 5 plus h quantity cubed. F of 5 is 5 squared. 25 divided by h. That's just substitution. We just substituted 5 plus h into the function. We also substituted 5 into the function. Nothing much going on there, but you got to understand what to do. You got to understand the meaning of the notation. Now what can we do? Well, do the only thing you can do. You got to just simplify the top, I guess. Just expand it out. Do some algebra, you could call, for this reason, or simplifying. 5 plus h quantity squared. Careful, though. It's really FOIL. It's really 5 plus h times 5 plus h. I've got to use the FOIL method. First times first is 25. Outside times outside is 5h. Inside times inside is 5h. So I get 10h plus h squared. Many people make the mistake of not putting a 10h in there. But that is absolutely essential. You'll get the wrong answer if you don't. The reason the FOIL method works, if you want to know, is because of the distributive property applied a few different times. You could work it out if you're really interested. 5 squared is 25. We're going to subtract 25. That's just algebra. The next step is just algebra or simplifying. I can divide, I can cancel the 25s. 25 minus 25 is 0. I can also factor out an h out of what's left in the top like this. That's just algebra. Algebra is a good enough reason. You could also call it simplifying or canceling and factoring. Those are different words you could use here. And they'd all be okay for me as far as reasons go. This next step, I'm going to divide out the h's. You might say, well, that's just algebra. But that actually is a bit more than algebra. Why is that a bit more than just algebra there? For the reason. It is algebra, but it's a bit more. Anybody remember what extra reason we gave here about a month and a half ago? This expression is not even defined at h equals 0. This one is. You're getting close. It's actually the next step that's related to continuity, but you're close. This does end up have this function, if you think of it as a function of h, does have a removable discontinuity at h equals 0. But more fundamentally here, the fact that these two limits are the same, if they exist at least, is the fact that the value of the limit doesn't really depend on what happens to the function at h equals 0. It really doesn't, in the abstract at least. In a practical sense, for continuous functions, it does matter. But when you define the limit, it really doesn't matter what happens at h equals 0. So one way to phrase the reason is you could say the value of the limit, assuming it exists, is independent of what happens at h equals 0 in the abstract. That's one way to give the reason, kind of a wordy way. You could also say, for short, you could say definition of a limit here. That epsilon delta definition doesn't even require the function to be defined at h equals 0, which this one's not. This one's undefined when h is 0. You can't divide by 0. But these two expressions are the same when h is not 0. So if this one has a limit as h goes to 0, then this one will as well. And here's the continuity. Now you do plug in h equals 0 to get 10 plus 0 without a limit sign anymore, and to say that's equal to 10. That reason is the continuity of what? Of 10 plus h at h equals 0. Think of h as a variable here when you're taking this limit. This as a function of h is a very simple function of h. It's linear. In fact, its graph is a straight line. No holes in its graph. You can evaluate the limit by substitution. That's a property of continuous functions. This one's not continuous at h equals 0. You cannot plug in h equals 0 there. You'd be dividing by 0. Your calculator would give you an error message. But these two are equal when h is not 0. So if this one has a limit at h equals 0, therefore this one will also, and they'll be the same. And this one's continuous, so you can plug in 0. This is fundamental stuff to truly understanding derivatives. There's different levels of understanding derivatives. There's this definitional understanding, calculational understanding like this. There are the rules to know, and then there's the applications to know, and how to interpret the meaning of the derivative geometrically and as a rate of change. All of those are real fundamental things to know about derivatives. Can I clarify anything else here? Please speak up if you've got a question. Probably somebody else has the same question. Mm-hmm.
Do we have to have a definition for the last equal sign?
Yeah. For a reason here, that's just arithmetic. Yeah, probably not on that one. 10 plus 0 is 10. or algebra, if you want to call it algebra, or simplifying. Okay. By the way, you can use a note card again, front and back for this test. Probably the limit definition should be on there, but you got to make sure you practice problems. Don't make my mistake that I made that I told you about last week when I was in grad school. I failed exams because I just tried memorizing stuff and hoped that that was enough, because my old practice exams were just felt too hard. I wasn't tenacious enough. I wasn't committed enough to really doing what I needed to do to pass it. Now those exams were 4-hour exams. They were super duper hard. I had the whole summer to study, and I was having trouble months trying to figure out these old exam problems. Okay, yours are not that hard. Okay, these are standard calculus problems. I'm not saying calculus is easy, but compared to that, it was not that hard. It was only when I finally practiced the problems and forced myself to get them that I passed. So we had derivatives as the definition. What about derivatives as, say, rates of change? On this old exam, it comes up in a few different places. Let's look at problem 11 next. The population P of Minnesota, millions of people, and T years after the year 2000 is approximated by this function of T. By the way, I believe when I made this exam problem, I actually looked up the data and I made this model based on the data. Based on this formula, the estimated population, or find the estimated population in 2019, including units, and figure out how fast the population is changing in the year 2019, including units. I didn't give this function a name. I didn't call it f of t. Of course, I could have. I could have called it g of t as well. There's different names you can use. You could pretend, you can abuse notation. Here, I will not mark it as wrong and write p of 19. Why is that abuse of notation? It's because p I'm using as both a dependent variable, a number, and a function name, when really just 5 minutes ago I said function names are not numbers. I said that for this problem, and technically speaking, for this kind of problem, definitely you should not treat f as a number. But when we think about applications, we get a little lazier about it. It's just common for scientists and engineers to do this, and think of p as both a variable and a function. The main thing is just not let it get you confused based on the problem type. It is sloppy notation. There's no doubt about that. It's not ideal to do this, but I won't mark it wrong in this kind of problem. Well, this is just a matter of plugging the numbers into the function. So we take 4.919 e to the 0.00754 times 19. Okay, so that's not a calculus problem. That's just an algebra problem, or a pre-calculus problem, you might say. Maybe you feel like figuring out 0.00754 times 19 first, thinking in terms of trying to get as much partial credit as possible on a problem. It might be good to go ahead and show that here, so that if you make a mistake, I can more easily identify where your mistake was. And if it's a small mistake, I can give you most of the points. Whereas if you just write down the answer and you get it wrong without showing any work, then I have no idea what you did. I mean, you may have just used your calculator and that's fine, but how do I know you're just not pulling something out of thin air, especially if it's wrong? So I can't give you as much partial credit in that kind of situation. I can raise e to that number like this. So again, aiming for as much partial credit as possible, I can write that as 1.1540291. That's an approximation. Then I can multiply by times 4.919. And now I go ahead and round, say, to 5.68. I don't tell you what to round to, and so just do something reasonable, and I'm usually okay with it. 5.68. What are the units? Is this people? 5.68 people? No, that wouldn't make any sense. Millions of people. 5.68 million people. Again, I believe I took the data from 2019 for this, so now here in 2021, it should be a bit bigger than this. You might wonder if this formula would still work in 2021, so I'd raise e to the 0.00754 times 21 power and multiply that by 4.919. If this is a good model, 5.76 million people would be the approximation for the current year. About 0.08 million people more than 2 years ago. 0.08 million is 80,000 people. 0.08 times a million is 80,000. Of course, this is a kind of, you might call it a crude model because it doesn't take things into account, like COVID. It doesn't take that kind of thing into account. It's just a rough estimate based on trends, you might say. Part B is where you actually do the calculus because you're trying to find out how fast it's changing, a rate of change, a derivative. You're trying to find dp dt. If we want to use Leibniz notation, evaluated at t equals 19. That vertical line and then writing t equals 19 means find the derivative first and then plug in 19. Don't plug in 19 first. If you plug in 19 first, you get a number and its derivative would be 0, but that's not what we're doing. We need to think about the function and differentiating it first before plugging in the 19. So the evaluating at t equals 19 is done at the very end. To differentiate this, hey, that you know how to differentiate that. Just use the chain rule. I'd get the constant times e to the same power. But then that's the inside function for the chain rule, 0.00754t. I need to multiply times the derivative of that inside function. That's the chain rule. Evaluated at t equals 19. If you multiply these two numbers, what do you get? 4.919 times 0.00754 gives you that. 0.0370896 e to the 0.00754. Now go ahead and plug in 19. It's fine. Times 19. 0.00754 times 19 again is that. E to that power is that. We did that before. But now I multiply by something different. I multiply by 0.037089 instead of 4.919 times 0.0370896. About 0.043. What would the units be here? Units of P per unit of T would be? Go ahead. Yeah, 1 million people per year. In other words, if you convert that to thousands, that's 43,000 people per year. Hey, and you double that, you get close to 80,000, like I was predicting for how much more it is in the current year. We could use this for a linear approximation, though that's not being asked here. Right, I said 2021, we're probably about 80,000 more than we were in 2019. Double this, you get close to 80,000. Closer to 90,000, so that would have been a better guess. But if we wanted a linear approximation, you should realize it would give you an underestimate because the graph here is concave up, and so tangent lines are below it. So linear approximations would give you underestimates that are too low. If we did use this, multiply it by 2, for example, to estimate the population here in 2021, by the change in population, be a bit too low. Okay. Sometimes these problems are not written with base E. Sometimes you might see it written as, say, I don't know, 4.919 times something a little bit bigger than 1 to the t power. The thing a little bit bigger than 1 actually would be e to the 0.00754 is 1.0076. That would be an alternative way of thinking about this model. 4.919 times 1.0076 to the t power is essentially the same model. If you differentiated this, remember, and you should know this for the exam, when it's not base E, but some other base, you need an extra factor of natural log of that number. 4.919 times natural log of 1.0076 times 1.0076 to the t power. And we don't need the chain rule there because it's a t power, but it does give you the same answer because this product right there does equal this number right there. Let's just double check that. ln of this number, that's the 0.00754 times 4.919 does give you 0.037089. But if I gave the model to you like this, you'd want to differentiate with a natural log factor. You should know that as well. That is something that we did talk about. Even had a quiz question about it. Any more clarifying that I can do there? You've been struggling with homework, quizzes, that's extra. That should be a signal that you've got to study extra hard. And the way to study extra hard is not just to read the book and write things down on your note card. It's to practice problems. And your note card's mostly there again just for helping with anxiety. Help you be a little bit calmer. But you should study enough if you want to do well, that you are confident you could do well without a note card. And that means you need to practice these old exam problems, time yourself even. Give yourself what we have for the class, an hour and 10 minutes, and see how you do. And you're going to get feedback. You'll feel the time pressure. You'll realize, oh, I really don't know this like I should. I'm just guessing here. You can feel it. Or you know that you're guessing. Maybe do it at the same time as a friend and compare your answers. They'll give you feedback about where you're weaker and where you're stronger. Look at 12 next, more rate of change ideas here. Temperature H of a cup of hot coffee is a function of time. H is in degrees Celsius, time is in minutes. Using units, explain the meaning of these statements. F of 5 is 40 and F prime of 5 is negative 1.8, and also approximate F of 7. Since we don't have any formulas here, evidently the only thing we can do is use a linear approximation. If you don't have formulas for things, but you somehow measured approximately what the rate of change is, which you can do with instruments, you can approximate, you can use a linear approximation. There are instruments to not only measure the temperature of something, but also how fast the temperature is changing. They measure the change in the temperature over a small interval of time to get an approximation to the instantaneous rate of change of temperature. Maybe you can even find a fancy thermometer that would do that. F of 5 equals 40. H is F of t. So compare these two things. The input is t equals 5 times 5 minutes. The output is 40 H in degrees Celsius. After 5 minutes, the coffee is 40 degrees would be an interpretation of that. 40 degrees Celsius. All right, that's the function interpretation. What about the rate of change? This is using function notation, f prime of 5. I can also write this with Leibniz notation. dh dt is what it would be, right? Because h is the dependent variable, t is the independent variable. Evaluated at t equals 5 is the same as f prime of 5 is negative 1.8. Before we write down what it means, let's just think about the units. The Leibniz notation helps you think about the units. It's units of h per unit of t. Just like you're doing a division, even though you're not literally doing a division. Degrees Celsius per degree per minute. Degrees Celsius per minute. At time 5, that's how fast and with direction the coffee is changing temperature. It's negative, so it's cooling. So you'd say now, at time t equals 5 minutes, the rate of change, you could also put the word instantaneous in there if you like. That's probably better, but I'd be okay with just rate of change. Rate of change of temperature with respect to, you can abbreviate WRT for with respect to, time is negative 1.8 degrees Celsius per minute. And now we can use that for part C to approximate f of 7. This is a linear approximation. This is like h nu. H nu, the temperature, the new temperature at time 7 is approximately f of 5. That's the old temperature, h old, plus the change in temperature, delta h. This is similar to what we did at the end of class on Friday, except the notation is not quite as nasty. The same idea, though. And that's approximately f of 5 plus what's delta h? It's the derivative rate of change times the change in time. Delta h, change in temperature, is approximately the rate of change f prime of 5 times the change in time. Now plug in the numbers. This is 40 plus negative 1.8 times, what's the change in time? Nope. From time 5 to time 7 in minutes.
2 seconds.
2 minutes.
Minutes.
2 minutes. So I'm glad you tried. 40 minus 3.6. So it's 36.4 degrees Celsius is the estimate for the temperature 2 minutes later. It's going down by 1.8 degrees Celsius per minute. Over 2 minutes, it goes down by about 3.6 degrees Celsius, 2 times 1.8. That's what we've just used there. It's not exact because the true graph is concave up. It's an exponential decay. In using a linear approximation, we're really using a tangent line to approximate the curve, but the curve is concave up, so the tangent line is underneath it. So the estimate's going to be too low. The actual temperature is going to be a little bit bigger than 36.4, assuming these measurements are correct here. Assuming I've got instruments that can measure these quantities, I use a linear approximation. This is going to be a little bit too small. You got to know that coffee cools exponentially, though, in order to know that. It does. You can test it. You do have to mix up the coffee, though, because otherwise you have to take spatial effects into account, and that gets extra complicated. Anything more that I can clarify there? So what have we done so far? We've essentially done a lot of stuff from chapter 2 so far today. Okay, just watch the recording after class. hopefully. Let's do some problems that are from chapter 3. We talked about derivatives as limits and as rates of change, and thinking about how they're tangent lines and relationships to the graph, whether concave up and concave down, linear approximations. That's actually also at the end of chapter 3. But now how about more in the middle of chapter 3? Differentiate that. Yikes, doesn't look so nice. I did put a derivative in fall 2019. I could put a derivative on your exam. I probably will. Even though we already have the gateway and still some people that need to pass the gateway. But some people did pass, but we're still, and you should practice derivatives still. It's a sum, just differentiate each piece and add the answers together. That's a composition. There's its derivative, because the derivative of 2x is 2. Derivative of tangent is secant squared. But my inside function is cosine 2x, so I need to differentiate cosine 2x as well. Multiply. I actually need the chain rule a couple times here, but there's what you would get. These parentheses are essential. The dot is somewhat optional, but parentheses are essential. Next term, I need the product rule. The derivative of 5x squared is 10x times the second function plus the first function. The derivative of natural log of x cubed would be 1 over x cubed times 3x squared from the chain rule. I'm going fast here, I know. That thing, I need the quotient rule. It's a quotient. Low, d high, yikes, this is getting nasty looking, minus high, d low over the square of what's below. X squared squared is x to the 4th. There's the answer. Wow. Kind of nasty. You should practice your derivatives. You should know your facts, even though you can put them on your note card. You should try to memorize them still. So you don't get bogged down. Practice, practice, practice. This is amazing. Do you realize how amazing this is? I don't think we appreciate this like we should. Very complicated function, yet we can still find the answer as long as you don't make a mistake. We can find its derivative. We can find its rate of change. We could graph these functions and the graph should make sense. Now the graphs might be really, really weird and nasty, but it could be done. That's astonishing. I praise God for that. That He has blessed us with minds to be able to figure this out, even though most of us couldn't figure it out from scratch, but we can be taught it. When I say most of us, I include me. Okay? Newton says, I stand on the shoulders of giants. There are people who came before Newton that he used their knowledge, and we're using knowledge of people like Newton and people who came after him. We can see further because we're standing on the shoulders of giants, is the way the metaphor goes. That's astonishing. Skip number 7 for the moment and jump to number 8. You're given some function values and derivative values here, no formulas. Part A, find h prime of 2 if h is this product. Part B, find h prime of 2 if h is this composition. Part C, part H, find h prime of 2 if h is this composition. This is the product rule. Let's just do B and C. This is the same as f of x to the 1/3 power here. It's a composition. There's an inner function, do f of x first, then there's an outer function, the cube root. You got to think order of operations. That stuff you learned about in 5th, 6th, 7th grade, order of operations, it comes in handy here to understand. Do the inside function first, the f of x in this case, and the outside function, 1/3 power next. And that affects how you think about it with the chain rule. H prime of x, the derivative of x to the 1/3 is 1/3 x to the negative 2/3 But then you plug in the inside function, and then the extra step is to multiply times the derivative of the inside function. Now plug in 2 and use what you're given. H prime of 2 is 1/3 f of 2 to the negative 2/3 times f prime of 2. Plug in the numbers. F of 2 is 8. F prime of 2 is -1. Can you do that in your head? 8 to the 1/3 power is the cube root of 8 is 2. 2/3 power, you'd square that to get 4. Negative 2/3 power means it's a 1/4. This is a 1/4 in disguise. If you're not sure, the calculator can give it to you as well. 8 to the negative 2/3 power is 0.25, 4. Or 1/4, excuse me. Times 1/3 times -1 is -1/12. There's the answer to part B. C, h of x is this, so that's a composition. H prime of x is going to be the derivative of the outside, g prime, plug in the inside, times the derivative of the inside. We're just using rules without understanding them. That's sometimes necessary. Plug in the number 2, so h prime of 2 is g prime of f of 2 times f prime of 2. What's f of 2? It's 8. What's g prime of 8? It's 3. What's f prime of 2? It's -1. The answer is -3. Just got to know your rules and be able to use them abstractly as well. Right? If you don't study enough, you're going to have no idea what to do here. You study, you think about what I just talked about. Maybe rewatch today's video, parts of it at least. I do put timestamps in them to help you find things in them if you want. If you want clarification on something. Yes, we can say, well, I don't really understand what's going on here in all these equations. That is true. We don't fully understand. That's often the case, that you don't fully understand a subject until later. But we can still use the rules. We can still understand how to use the rules. I skipped part A here, but that would be the product rule. That's a chapter 3 kind of problem. Let's do number 7 next. Another chapter 3 problem. We did a problem like this in class, so maybe shortly after spring break. F of x is a cubic. If you happen to graph it on your graph, this may be even the exact same problem I did. You'll see it'll look like about like this. F of 2 is 13. This is not to scale. Okay, a very, very rough graph. F of 2 is 13. Why? Well, 2 cubed is 8, plus 4 is 12, plus 1 is 13. Plug in x equals 2 there. F is invertible. It passes the horizontal line test. No horizontal line goes through it more than once. It's got an inverse function. What's the formula for the inverse function? Well, it actually is possible to find because it's cubic, but the formula is super duper nasty and there's no way I don't want to write it down. But we can still do these things right there based on things we know in calculus. And we could still graph the inverse function again, though it's tricky. You've got to imagine reflecting this across the line y equals x. And again, it's not to scale, so this is definitely far from perfect picture. It looks something like this. That's f inverse of x. We're plugging 13 into it. What do we get out? What's the answer? You should be able to just look at this if you understand the ideas. What's f inverse of 13? Go ahead. 2, yep. Why? Because f of 2 is 13. So f inverse of 13 is 2. They undo each other. If f maps 2 to 13, then f inverse maps 13 back to 2. Geometrically, these points here and here, if my picture were better, are reflections across the line y equals x. My picture is not perfect, and so it doesn't really look like it. So if the coordinates of this point are 2, 13, the coordinates of this point are going to be 13, 2. You have to give a reason. You could just say since f of 2 is 13. That's the reason. What's f inverse prime of 13? There's a formula you probably should go ahead and put on your note card. It would be 1 over f prime of f inverse of 13. That's what the formula would say. We did talk about this in class. I think it was after spring break. In that week after spring break, I think. But hey, this is 2. This is going to be then 1 over f prime of 2. So you got to find f prime of 2. So differentiate f. Get 3x squared plus 2. And now plug in 2. Get 1 over 2 squared is 4 times 3 is 12 plus 2 is 14. 1/14 is the answer. Geometrically, if this means what we found is the slope here of this tangent line is 14. Slope equals 14. It should make some geometric intuition that the slope of this one would be 1/14. It's a symmetric kind of picture. The rise of a run for those two lines, the slope is going to flip. How did we derive this formula? We used the chain rule. We actually did derive it. And that's something to make sure you study as well. How we derived this formula. It was based on the chain rule and the fact that f of f inverse of x equals x. We differentiated both sides of that equation and solved for the derivative that we wanted to find with the chain rule. We had to use the chain rule on the left, not on the right. Look in your notes, okay? It should be there. If you took notes, which I've been having you taking notes, so it should be there. Take a breath, we're almost done. Implicit differentiation was a problem, something we talked about. I'm gonna go really quick here. What do? We're trying to find dy dx, the slope. Dy dx. We need to assume y is a function of x. Use implicit differentiation. You assume this equation defines implicitly y is a function of x. So when you differentiate it, when you differentiate negative y cubed, you do not get 0. You do not get negative 3y squared. Instead, you get negative 3y squared times dy dx. Why? Because y depends on x. You could replace that with an f of x if you preferred, and that would be okay, even though you don't know what f of x is. With this next term, we've got a product of two things. I need the product rule. The derivative of x squared is 2x times the second function plus the first function times the derivative of the second, 2y dy dx. The derivative of 11 is 0. Solve for dy dx here. It's an algebra problem now. You'd have to subtract 3x squared from both sides, subtract 2xy squared from both sides. You'd have to, with the dy dx terms on the left side, you'd have to factor out a dy dx before dividing. You'd want to solve for dy dx, and to solve the problem, to find the slope, you'd want to plug in this point, x equals 2, y equals 1, to get a number for the slope and an equation for the tangent line. You had homework problems like this. We did do examples like this in class. I'll let you finish it. I don't know if I'll have time to put answers to this up on Moodle, but you can compare with other people in the class. You could also go to Math Lab, see if they can help you determine the right answer. Let's look at this page now. You don't have to do anything with infinitesimals on your exam. I did do that with fall 2019 because I emphasized that more in the lectures. That will not be on your exam. But a problem like this could be approximating the fourth root of 85 in two ways. In part A, it's with local linearization, also known as linear approximation, also known as tangent line approximation. Part B, it's with Newton's method, like in the project. It looks long and hard to read. That would be a lot to read, especially in the time pressure of an exam. You need to practice this kind of problem, and even more than just my examples, make up your own examples. Similar, just modify them and practice. Otherwise, in an exam, you're going to get scared by this, right? The anxiety builds like, oh boy, I have no idea what this is talking about. If you practice, you won't have that kind of anxiety. You'll know what to do. Part A or part 1 here, show work that confirms the answer L of x is this. L of x is just the name of the linearization function. Its abstract formula, you can write f of x is approximately L of x. L just stands for linear. It's f of a plus f prime of a times x minus a. In our class, I don't think I've used the L of x before. I'm doing it now because it's in the exam. L is just the name of this new function. That's all it is. L for linear. You got to plug in the numbers. What is A? A is 81. We're going to have to find f prime. We can do that. F prime of x to the 1/4 power is 1/4 x to the 1/4 minus 1 is negative 3/4. Plug in A. A is 81. What's f of 81? What's the fourth root of 81? Should be able to do that in your head. I made it nice. Fourth root of 81 is small number 3. 3 to the fourth is 81. F prime of 81. I need f prime of 81. That's 1/4. 81 to the negative 3/4. Yeah, you could use your calculator, but you could also just think about it. 81 to the 1/4 is, like we just said, 3. So 81 to the 3/4 is 3 cubed, 27. And your calculator will confirm that. And yeah, that's 108. So this is 1 over 108 times x minus 81. I told them the answer, and they're just confirming it. Second part. Use L of 85 to estimate the fourth root of 85 to 5 places after the decimal. Though it may not be accurate to 5 places after the decimal. F is the fourth root function, so the fourth root of 85 would be f of 85. By this formula, that's approximately L of 85, which is 3 plus 1 over 108 times 85 minus 81. That's a 4. 4 over 108 would be 2 over 54, would be 1 over 27. 3 and 1/27, or as a fraction, it's 82 over 27. Because 3 is 81 over 27. 82 divided by 27. 3 and 1/27, so it's about, the 5 decimal places, 3.03704 if you round. Now that might not be accurate to that many decimal places, but it's just rounding this number to that many decimal places. The error in part 3 here is actual minus approximate. Remember that? actual minus approximate, E of 85. The error at x equals 85, not ethanol 85. That's a little joke. Maybe a bad joke. Is actual minus approximate. What's the actual? Well, we have to approximate it. 85th to the 1/4 power. 3.03637 minus 3.03704. It's going to be a negative error. Close to 0. Negative 6.7, say, times 10 to the negative 4, which you can also write as negative 0.00067. And it's negative because the approximation is a bit too big. And why is it too big? It's because the graph of the fourth root function is concave down when x is positive, and so the tangent line is above it, which makes the approximation too big and makes the error negative. Hang with me here. We'll only have time for just this now. Do it with Newton's method. Notice the f of x is different. Why? Because that's how you do Newton's method. The fourth root of 85 is going to be a 0 of this function, right? F of 85 is going to be 0, a fourth root of 85. We apply Newton's method to this function. Newton's method iterates a new function, g of x, that is x minus f of x divided by f prime of x. That was in the project. X here is x to the fourth minus 85. Its derivative is 4x cubed. That's the function we need to iterate using a guess of x0 equals 3.1. x1 is going to be g of 3.1. I say use Newton's method once with the details of the calculation. I could have also asked them to hit enter a few different times and get a better approximation, but let's just see what this gives. I'll type in 3.1 here. That's my x0. I need to type that formula into the calculator by using the ants feature. You don't have to do it with the ants. You could just type the numbers in. But this will allow me to keep hitting enter and keep getting better approximations if I ask for that. Got to be careful to use parentheses. X to the fourth would be ants to the fourth minus 85. And don't make a mistake like that. Divided by, use parentheses again, 4x cubed is 4 ants cubed. So if I hit this once, that should be the answer for the problem, 3.03830. If I hit it again and again, I'll get better and better answers. And in fact, you only need to hit it a few times for it to be stable to 1, 2, 3, 9 decimal places. And if you raise that to the fourth power, the calculator does approximate it to 85. Okay, and I could have asked that. What have I missed? There are some things I've missed. I've missed practicing the product rule. And, well, I guess we did do that. I'm sure there's some main things I've missed here I haven't had time for. I'll try to highlight those in maybe an email or something. Have a good day. Do you have a question? Yeah, you can look at your gateway. You just need to come to my office.
Professor Kenry,
Not enough time to do it here.
where can I find the video?